The 13th video on simultaneous equations introduces Gaussian elimination. So previous videos then have demonstrated that pre-multiplication of equations in matrix form can be used to change something like ax equals b into a row echelon form. This video looks at systematic techniques for choosing the appropriate pre-multiplication matrices, or equivalently, the appropriate row operations. This technique is analogous to the sort of standard methods for solving simultaneous equations that you do on pen and paper, but here we need to be a bit more systematic so we can automate it with computer code. So just a reminder of what we're saying if you have original equations of the form ax equals b, equivalently you could solve the expressions dax equals db as long as d is full rank. Or you could indeed have a number of pre-multipliers, fed times ax equals fed times b, as long as fe and d are full rank. And so our goal is to find a sequence of pre-multipliers so that when we multiply a, we end up with just I, and then we get ix equals fedb. Now, the key thing you need to remember is these matrix multipliers are equivalent to row operations on A. So in fact, we're never going to define the matrices F, E and D, we're just going to define the row operations. We'll do the row operations on B, and the end result is we'll find X. So just a reminder that pre-multiplying or multiplication on the left by a matrix D is equivalent to a row operation. So you'll see if I multiply A on the left by D, whose first row is 1, 0, 0, then the first row of dA is going to be the same as the first row of A. If I look at the second row of D here, which is minus 1, 1, 0, then the second row of dA is going to be the second row of A minus the first row of A. And finally, you'll see this third row, 2, 0, 1, is going to say that the third row of dA is the third row of A plus twice the first row of A. But the key thing you see is that multiplying on the left by D does row operations. So I'm going to focus on choosing row operations and leave the fact that there's an implied D as implicit, but we'll never actually write what that D is. Principle 1 then, first steps. We need to rearrange the rows and columns of the matrix in order to optimize the use of any zeros which are already present. Now it's difficult to state how this should be done in a unique mechanical fashion, so here we're going to illustrate the principles only. And there's a warning down here, quite an important warning. If you swap the columns in A, then you're changing the order of the variables are stored in the vector x, so don't forget to do that. We'll illustrate that in some of the examples. So here, imagine this is our matrix A, and what we want to do is optimize the use of the zeros. You'll see there's a number of zeros in this, and we want to optimize the use of those zeros. So the first thing we're going to do is swap column 2 with column 4. Okay, so you'll see column 2, that's this column, column 4, that's this column. We're simply going to swap those two columns. And now I'm going to swap row 2 and row 3. And now I'm going to swap column 2 and column 3. And what have I ended up with? You'll see here that now I've got an upper triangular matrix. So obviously this was a fixed case, I specifically made it like this, but the key point you can see is with appropriate row and column operations I can turn this into a row echelon form. So we've converted the matrix to row echelon form, and thus the variables can now be solved efficiently. And we used only row and column moves, which thus involve negligible computation. However, in general, row and column swaps will not achieve a row echelon form, but we can use some swaps in order to position the zeros in the most useful part, and normally we're going to target the lower left part, so we want as many zeros in the lower left part as we can get. Right, the second principle then, handling row operations. So you're reminded that a row operation is equivalent to a pre-multiplication by a full rank matrix D. In general, it's easier to handle the fact that we're multiplying the D on the A and we're multiplying the D on the B by creating this augmented matrix, which is A and B stacked together. So then you can write D times AB, which is equivalent to DA dB. So hereafter, the augmented matrix will be used, and it's recognized that the last column corresponds to the B component. Now, how are we going to choose the row operations that we want to use? We're going to basically do this the same way you solve simultaneous equations on paper, which is we're going to try and eliminate one variable at a time. And the way to do this is to consider that each column corresponds to a different variable. So the first step is to set the first column to be 0 except for the top row. So all the coefficients in the first column should be 0 except for the top row. And then what we're going to do is look at the second column, and we're going to say all the coefficients in the second column should be 0 except the top 2 rows. And then we're going to look at the third column and say all the coefficients in the third column should be 0 except the top 3 rows, and so on. And hopefully it's obvious that what we're doing here is creating a triangular matrix A, upper triangular. Now, I'm not going to worry about the details you'll notice in this box at the bottom. Advanced code may well try to look for the largest coefficients in order to improve numerical conditioning, but I'm not going to focus on that level of detail. So here's an illustration. First thing we do is we take our A and our B and we form our augmented matrix AB. So you'll see I've done that here. Now what I'm going to do is look at a row operation. So I'm going to pre-multiply or do a row operation so that row 1 is unchanged and row 2 becomes row 1 plus row 2. So if I do that with this augmented matrix, you'll see here row 1 is unchanged, same as it was, and row 2 is row 1 plus row 2, and the key thing is I've now got this 0, so you'll remember my technique was to start with the first column and say all but the top row should be 0. So I've achieved that. So now, using simply row operations, I've created the row echelon form that I need. And of course this is now equivalent to 1, 2, 0, 5 into x, y equals 3, 4. And you can solve with back substitution. What about the second one then? So here's the second example. We've now got 3 variables. The first thing to do then is to create this augmented form, and you'll see all I've done is basically stack A and B together. Now I'm going to look at row operations, and my first objective is to create zeros in the first column. So I'm going to do that by saying row 2 becomes 5 row 1 plus row 2, and row 3 becomes row 3 minus 2 row 1. So if I do that, what do you notice? I've now got 2 zeros in the first column, but not on the top row. So the next thing I want to do is create zeros in the second column. So I do that by updating row 3 to be 6.5 row 3 plus row 2. And now you can see I've got my upper triangular form. I've got the zeros I need in the bottom left hand side. So now we're in row echelon form. We can easily solve. We can solve for z from the bottom row, then we can solve from y using the second row, and from x using the top row. And they're the equations. Third illustration. Now the difference with this third illustration is you can see we've got lots of zeros in the matrix. So the first thing we want to do is say, can we exploit those zeros? So what I'm going to do is swap columns 1 and 2. Now you'll notice because I've swapped columns 1 and 2, you'll see the y and x have swapped positions. So I need to remember to do that to say that my state variable is now ordered differently because I've swapped the columns. Next thing I'm going to do is swap columns 2 and 3. And now you'll notice, of course, the W and the X have swapped positions. And now I'm going to swap rows 2 and 3. Now, obviously I haven't achieved a row echelon form because I can't do it with this one, but you will see that I've got lots of zeros in this bottom left-hand corner, and that will make all the computations I have to do later much quicker because I've already got lots of zeros, so I don't need to do computations to make those terms 0. So what I'm going to do now is create my augmented matrix. So this is what I've got after all my row and column operations, and you'll notice I've reordered this state vector, so it wasn't what you had originally. And here's my augmented matrix where I've added the B vector on the right hand side. So now I've got to look at the first column and say, how can I make zeros in the first column? So it's only row 4 I've got to deal with, because I've already got 2 zeros here. So row 4 goes to 2 row 4 minus 5 row 1, and there we go. You'll see we've now got zeros entirely in the first column. And now we need to look at the second column, and again we only have to worry about one row because we've already got the 0 we put there before above that. So we do that, and now you can see we've got zeros in the second column. And then finally we make zeros in the third column. And there we go. So you see once again we've got our lower triangular form, all zeros in the bottom left. So now we need to solve it. So what you'll remember is this is where we started after we'd done simple row and column operations to get the zeros in the right place. So that was the augmented matrix we started with. This is the augmented matrix we finished with, which is equivalent to this matrix times my state vector equals this right hand side. So I've gone from the augmented matrix back to the matrix form just so that you can see what's going on, and now it should be obvious. I can solve from Z from here, I can solve for X from here, I can solve from W from here, and then I can solve for Y from here. And there's the expressions if you want to check them for yourself. Now a comment, while you are learning you can use MATLAB to check all your calculations, and so you'll see here I've put different A's and B's and shown that you can actually calculate the solutions using simple inverse of the A matrix times B, and you'll notice here I've been very careful to actually note that the answer has got the variables stored in a different way. The first one is X then Y then W then Z, and the next one is Y then W then X then Z, and if you see that here you will see that swapping has taken place. So a summary. Gaussian elimination involves 2 key steps. Make the most use of existing zeros by swapping rows and columns to place the zeros in the lower triangular part. Use row operations beginning with column 1 and move sequentially to column n to place zeros in the entire lower triangular. So remember, you do all of column 1, and once you finish column 1 you then do all of column 2, and once you finish column 2 you then do all of column 3, and so on, and you'll notice that then becomes easy to code. Once the equations are in row echelon form, back substitution can be used to find the solution.